Notes 13, page 2, one review of dividing rational expressions, and then we're going to move to adding and subtracting. I did want to review basic arithmetic. Part of the problem that students struggle with rational expressions when they get to algebra is because, yeah, you learned how to divide fractions, but pretty quickly you said, oh, just use a calculator. So you've forgotten a lot of the details. So I'm doing multiple steps from here to here. When you're dividing, when you're trying to cancel, you can cancel factors. So I took the 12 and I factored it as 4 times 3. I took the 35 and factored it as 5 times 7. Then I changed the division to multiplying by the reciprocal. 25 was in the denominator. Now you see 5 squared in the numerator, so I factored that as well. And 8 was in the numerator. It's now in the denominator, 4 times 2. Now, only difference here between rational expressions and fractions, and actually this can happen with rational expressions here, 4 is not prime. But since there's a 4 down here, I can go ahead and cancel them. Cancel the 4s. One of these 5s cancels with one of those 5s. Nothing else is going to cancel, so I have 3 left in the numerator, 7 times 2, 14 in the denominator. Okay, that's how you learn to divide fractions in grade school. Unfortunately, it's been a while since you've done it, but we are doing the exact same thing when we get to rational expressions. So I'm going to look at this, and I realize this is one big fat term. I'm trying to simplify within this term. I want to do the division and I want to reduce. So what I need is I need factors. And I need to flip, which is multiply by the reciprocal. So it's factor and flip, factor and flip. And you can do them both at the same time, or you can do the factoring first, or you can do the flipping first. It doesn't matter. Because of space, I'm going to try to do them both at the same time. So I'm going to factor this numerator. First step in factoring, don't forget, don't make this hard. What is it? GCF, 2x. And that would give you x plus 5. Okay, now, I started you off on this. What I'd like you to do is pause the video and try it, and then turn the video back on to see if you got the right answer. You really will do better if you try these on your own and then check your answer. So I'm going to go on. The 7x minus 1, I can't factor that, so I scoop it in parentheses. There it is. Now it's a factor. All right, the division becomes multiplication, but this denominator, will flip to the numerator, but I'm going to factor and flip at the same time. This is the difference of 2 squares, because the square root of 49 is 7. So this is 1 minus 7x times 1 plus 7x. And then this numerator is going to become this denominator. I'm going to factor it. No GCF. Does look like it comes from FOIL, quadratic, constant, linear. So that would be open 2 blank parentheses. The answer is probably a binomial times a binomial. I know first times the first is 2x and x. And that's the only thing I know for certain. I do know because that's negative, it's 1 plus 1 minus, but I'm not sure where that goes. My options for 15 are 15 and 1, which seems highly unlikely because I think that would be a big middle term. There's 1 and 5. It's not 1 and 5, 3 and 5. And I'm thinking 5 times 2 is 10. 10 minus 3 is 7. Notice I'm thinking 10 minus 3, not 10 plus 3. That's because I know it's 1 plus 1 minus. I know the outer and inner will subtract and not add. So if I put a 5 here, that's 10. If I put a 3 there, that's 3, and this will give me 15. I want the 7 to be positive, so if I put the plus here, that's plus 10, minus 3 will give me 7. All right, so notice, if you miss factor, then you miss these problems. All right, so let's see if we have any identical and opposite factors. I see the x plus 5s. And then the 1 minus 7x and the 7x minus 1, see how they're flipped around the minus sign? When you flip numbers around a minus sign, you just get opposite answers. So those are opposite factors, so they cancel to a factor of -1. Make sure you indicate it's multiplied by -1. Cancel that. And then I think that's it. So it's -1 times 2x, so that's just -2x. And this annoys me. I'm going to change that to 7x plus 1. 7x plus 1 all over 2x minus 3. One comment about the answer. Notice how I didn't put parentheses around the 2x minus 3. Since that's the only factor down there, I don't have to have them, because remember, this fraction bar is understood parentheses, so they are understood to be there. So you can have them there or not. You better have them around the 7x plus 1 though. All right. So that's multiplication and division. It really is factor, cancel identical factors, cancel opposite factors. There's nothing more to it than that. Addition subtraction is actually harder with fractions. And there's a whole lot of basic ideas in addition subtraction that you really need to be good at and really understand to be able to work with adding and subtracting rational expressions. So I'm going to review some basics here. Remember, when you see addition and subtraction, that is, you have multiple terms, you basically have multiple terms of piles of objects or types of animals, and we can only combine two terms into one term or one pile if both the piles have the same sort of thing in it. So dimes in one pile, dimes in another, you can throw that into one pile of dimes. All right? The denominator of a fraction tells you the value of the coin. It tells you kind of like the type of animal. The numerator simply counts how many of that object you have. So it's very similar to something like 3x. X is the type of term you have, and the 3, the coefficient, tells you you have 3 of these x's. For instance, 3/4 says you have quarters because the denominator is 4. The numerator says you have 3 of them. And then we can actually compare this 3/4 to the expression 3x and say, well, what if x was a quarter? This would say I have 3/4. And we know to multiply fractions, you just multiply across, it's 3/4. So the numerator counts how many, the denominator tells you what size, and one little add-on here, if I had 3/4 in one pile and 2/4 in another pile, the quarters are telling me this is the same value of coin. The 3 tells me how many are in this pile, the 2 tells me how many are in this pile. Once your denominators are the same, you have like objects, you have the same coin, you just count how many you have, and that means you just add the numerators. That would be 5/4, but they are still quarters. So it's really very similar to 3x plus 2x. Once you realize the x's are the same animal, they're like terms, you just add the coefficients, but it's still 5x. All right, so very basic stuff, but you do need to remember it. Now, we are going to go over this addition problem with regular numbers. And I won't ever give you anything like this on the test, but everything we do for this problem is what we're going to need to do for rational expressions. So, to add rational expressions. So, when you have two terms and you want to combine them into one pile, they have to be like terms. In this case, with fractions, To be like, that means they have the same denominator. They're the same value of coin. So to add or subtract fractions, to put them into the same pile, you need a common denominator. For most of the fractions we've been working with, most of you could eyeball the common denominator. But there are times when the common denominator is not easy to find, and that's going to be the case when we start dealing with x's and y's. So I want to review this process of finding a common denominator when you can't quite tell what it is. We build the LCDs, least common denominator, from prime, it's really important, prime factors of the denominators. So if I want to figure out what's the common denominator between 60 and 72 here, I've got to factor 60 into primes. Now, I did this very quickly, but 60 factored into primes is 2 squared times 3 times 5. And I have to factor 72 into primes, which is 2 cubed times 3 squared. It's these factors here that we will build the LCD from. We're trying to build a number that's as small as it can be, but big enough that both 60 and 72 can divide into. And the way we do that is, well, if I want 60 to divide into my number, I better have 2s and 3s and 5s in my LCD. So notice I have 2s and 3s and 5s. And I need 2s and 3s for the 72. Got them. So I'm going to need to have 2s and 3s and 5s in my LCD. How many 2s? Because this is 2 squared, this is 2 cubed. Do I need 2 to the 5th? No. If I have 2 cubed, which is the larger exponent, if I have 2 cubed, I also have 2 squared. So the rule for building the LCD, when you have the same factor in your two original denominators, you use that factor but with the largest exponent it shows up. Okay? And so now we look at the 3's. That showed up in both denominators. That's a 3 to the first, 3 squared. I don't need 3 cubed. If I pull 3 squared into my LCD, I've also pulled a 3 to the first. So my LCD is 2 cubed times 3 squared times 5, which is 360. Okay? Now, really, it's best to work with this prime factorization for the next step. So I'm going to try to get both denominators to be 360. Well, I'm allowed to multiply a fraction top and bottom by a number without changing the value. So I have to go 60 times what is 360. Now that one's pretty obvious, okay? It's 6, but if you didn't see it, and this is what we're going to do with the algebraic expressions, notice the 60 has a 2 squared, a 3 to the first, a 5. The LCD has a 2 cubed, a 3 squared, and a 5. What's the 60 missing? It's missing 1 2 and it's missing 1 3. So if I multiply 60 by 2 times 3, that should give me the LCD, which is 360. So I would multiply this top and bottom by 6. Okay? And this fraction is now 6 over 360. Plus, okay? Now, to me it's not real obvious, 72 times what is 360? Well, use the factors. Here are the factors of 72. Here are the factors of the LCD. 72 has 2 cubed, LCD has 2 cubed. I don't need any more 2's. 72 has 3 squared, LCD has 3 squared. I don't need any more 3's. 72 doesn't have a 5. I need to multiply 72 by 5 and punch it out in your calculator. It will give you 360. So this would be plus 5 over 360. Okay. And before we go on, we need 60 to divide evenly into 360 so that I can answer this question, 60 times what gives me 360? If 60 didn't go in evenly, like it went in 5.27 times, what would I multiply 60 by to get 360? That wouldn't work so well. Same thing with 72. I need 72 to go evenly into 360 so I can tell what I have to multiply 72 by, and I want that answer to be a whole number. So if 72 doesn't go evenly into 360, I wouldn't be able to answer this question. All right, so that's what an LCD is. An LCD is trying to the smallest number that both your original denominators will fit into. Once your fractions have the same denominator, it's like I have 6 of these, plus I have 5 of these same things. You just add the numerators. That's 11 of these things, which are 3/60ths. All right, that's the actual process for adding fractions. And now we're going to use that with algebraic expressions with x's and y's.